Hello and welcome to another video. In this video we're going to be doing a deep dive on heaps and HeapSort. So I've been doing these practice questions, and then whichever ones I find interesting I'm going to make videos on, and then most of the React ones that are interesting. So in this one you want to make a function that performs a heap sort. The function should take an array of integers and return an array of integers sorted in ascending order, and it's modified in place. So essentially it's sort an array using a heap sort. And then they kind of tell you like what a heap is and what a max heap is and so on and so on. So I'm going to do a deep dive on this. So we're going to build a min heap. As a follow-up, you can try to build a max heap or a custom comparator heap. Those also work. So essentially you can make a heap with a custom comparator to show how you should sort your values. And heap's probably like one of the more advanced basic data structures you want to know. So you do have to know it, and it is good to build it from scratch once or twice just to really solidify like what it actually does under the hood. And in a bunch of languages, heaps don't exist. So we're going to go over a heap and three common functions for it. And also one of those three is not talked about a lot, but I think it's pretty important. And I think it's only actually built in Python. So okay, so let's start off with like what a heap is. So a heap is basically an array under the hood. And what a heap does, or we're going to go over what a min heap is, and then the other heaps are just the opposite. So a heap is let's just write down some properties here. Complete tree, binary tree. So binary means each node can have 2 children max. Complete means I'm going to have nodes, and once I don't have a node, like let's say I don't have a node here. Like let's say I'm just done here. Wherever I don't have a node, I can't have anything else to the right. So none of this can be filled out, and then none of this can be below. So essentially, you fill it out level by level, and then whenever you're done, you stop. So like this wouldn't be complete because here you don't have nodes, but here you do. So an example of a complete binary tree would be like, let's say these nodes are missing. You can fill it out level by level, and then once you stop, you don't put anything else, right? So you fill it out like this. This is complete, and then we're done, and then we don't have anything else here or below it. So that's an example. And a heap has properties depending on min heap or max heap or whatever it is. And the property is, for a min heap, and max heap would be the opposite, is the parent value is less than or equal to values of children. So whatever value I have here for a min heap, it can't be bigger than values below. But it's not necessarily like a completely sorted BST or anything like that. It's literally just that one thing. So essentially, if I have a value here like 5, I can't have a value less than 5 here. The children have to be bigger or equal to the parent. So like maybe I'll have a 6 here, 10, whatever. And that's literally the only property you have. So this could be like one of these can grow way faster. This can be like 1,000,000 and whatever. So those are essentially the properties of a heap. And a heap under the hood is built with an array. And the way I do it, a few ways of doing it. Let's actually take this and bring this up. So the way I like to think about it is the root is node 0. And then all of these children are basically, you can number them. So they'll just go in order. So 0, 1, 2, 3, 4, 5, 6, and so on and so on and so on and so on. And the children of a node can be calculated. The left can be the node value, or whatever this index is. So index times 2 plus 1, and then the right is index times 2 plus 2. So just to double check that, so like let's say here this is 1, so the left would be 1 times 2 plus 1, which is 3, and this is 1 times 2 plus 2, same thing here, 2 times 2 plus 1, 2 times 2 plus 2. And yeah, so for a complete tree, essentially this always works. You can use this for other trees that aren't heaps, but also this is how your underlying array will work. So element 0 will be this node, element 1 will be this node, element 2, element 3, and then whatever elements I'll have, right? So if I end at some point, and so on, it'll basically be that. So let's just take an array of 10 items that aren't sorted at all, and let's just like show how to put them in a heap, and then let's actually go through one of the common things that isn't talked about for a heap and show how to build an array into a heap. So let's just have random numbers like 6, 8, 12, 3, 5, whatever. Okay. So if we actually put this in the heap, so essentially we can take these indices and use this. So if we take these indices and use this will be like 6, 8, 12, 3, 5, 24, 67, 5, 0, and 90. And then these are basically don't exist, so we can get rid of all of these. So yeah, so it's going to be in an array, but the tree helps you visualize everything. Okay, so essentially the goal here is to make it so this is clearly not a heap right now because we have elements that are, like for example, the 0 should be at the top, and it's clearly not. So the first function we'll go over in like pseudocode is heapify. And what heapify does is it takes an array and turns it into a heap in O of n time. So most people are familiar with like heap pushes and heap pops, and you can make a heap in O n log n time if you just push on all of these values. But the better way to do that is basically take an array and then do a heapify in O of n time, and then I'll turn it into a heap. And heapify is pretty simple. So all you do for heapify is you take every node that doesn't have children and you bubble it down. And what I mean by bubble it down means you compare it to its children. For a min heap, you take the smaller of the two children, you put it in its place, and then you just keep recursing down to like the very bottom. So like in this case, this node here, we're gonna be here, and we're gonna say, okay, what's the smaller of the two children? 0. And if the node is already smaller than its two children, then we're basically done with that node. But here, so we put a 0 here and we swap. And then because we did a swap, we're gonna recurse down here, and there are no more children here, so we're done. And then we go to the next node with, we go level by level. So this is the next node with a child. So this node has a child, but this is already smaller, so we're done. This doesn't have a child, this doesn't have a child, so now we go here. So same thing here, we swap this node with the smaller of its two children, which will be 8, 0, and we recurse whichever way we swapped. So because we swapped this way, same thing, we swap it with the smaller of its two children, and then there's no children here. So same thing here, this is already fine. And now last one here, so swap it with the smaller of its two children. So go down, swap it with the smaller of its two children. And then swap it with the smaller of its two children. And then we're done. So now this satisfies min heap. So essentially, to recap, go node by node, starting with nodes that have at least one child. Swap with smaller of children and recurse down for each. And that's essentially what heapify does. And so this like starting at a node and swapping with the children and moving down is actually, there's a name for it, it's called bubble down. So essentially you start at some node, you swap it with the smaller of its two children, and you keep recursing down. It's called bubble down in a heap. So with a heapify, we're gonna code bubble down, and then we're just gonna call bubble down on every node that has children, and then that will give us a heap. The next thing we need is we need a heap pop. So heap pop, pretty simple. It pops off a node, pops off. So the other thing is in a min heap, the smallest value is guaranteed to be at this index 0 because it has to be smaller than all of the children. So we pop off the top node. Then we replace it with a last node in the heap. And then we bubble down from there. So we're going to use the bubble down that we already made. So what does that look like? So we're going to pop off this 0. Yeah. And I can actually show how we're going to end up sorting this whole array. So we're going to do this for all of these nodes really quick. Okay, so we're going to pop off this node. We're going to place it into the array because this will be the smallest element. So we're going to pop this off. and then take the very last node we have and put it up here. So the very last node is actually this node. This is going to be at index 789, this guy right here. So we're going to put 90 up here. Now this is gone. Okay, now we go from here and we bubble down. So swap it with a smaller if it's 2 children. Then swap this with a smaller if it's 2 children. Here it doesn't matter which one, so let's just go right. Okay, now this is a heap. Then we're going to do the same thing. We're going to pop off the top, smallest element. Replace it with the last element in the heap, 8. And bubble down. So 8, we're going to swap it with a 5. Swap it with a 5. Swap this too. And then this is a good heap. So same thing. Pop off the 5. Put it here. Put the last node in here. And swap it over here. And swap over here. So that's good. Now we pop off the top again. Put in the last node, just 67. Get rid of 67. Swap it this way. And swap this way. Okay. Then pop off the 6. Put in the 24. Get rid of that. Swap with the 8. And we don't need to do any swaps. Then pop off the 8. Put in the last node here. Get rid of it. And then swap like this. Then 12. We put 67 up there. 67 swaps here. Pop this guy. Put 90 up there. And then same thing. So swap, pop, and then we just have the 1 node left. So this is like the idea of heap hopping. You don't have to keep heap hopping, but essentially heap hop follows a bubble down. We pop a node. So we pop a node, we put in the last node, and then we bubble down. And this is log n for each pop. And hopefully that makes sense why, because we're essentially going from the root, and worst case, we have to go all the way down the tree. And it's log n because the height of the tree is log n because it's a complete tree, it's a balanced tree. But this is kind of the thing we're going to be doing. So essentially we're going to go code up bubble down and then code up heapify. So we're going to use heapify to make a thing right away. And then the last one to mention is heap push. We're not going to code this, so I'm just going to explain it. So heap push basically adds a node to the heap. In heap push, instead of bubbling down, we bubble up. So let's just say we have some random heap. I'm not going to put in numbers here. So let's just say we have a heap. Looks like this. Actually, let's put in some numbers, I guess, quickly. 1, 10, whatever, some number. Okay. All right. So the way a heap push works is we add a node to the very end. So wherever the next available slot is, in this case, it would be here. Whatever node, let's say we add like 0. And then we do the opposite of a bubble down. So instead of bubbling down, we bubble up. So we go all the way up the path to the root. And then if we ever need to do a swap, we do a swap. If we don't need to do a swap, then we're done. And we need to make sure that like the element we're on is smaller. Or actually the element we're on needs to be greater than or equal to the one above it, right? Because that's the heap property. So like here, you'd have to do a swap. So 3 would go here, 0 would go here. Then you go here, do a swap again, and then do a swap again. So it's basically the opposite of bubble down, except we just bubble up. And it's also log n, and you can code that one if you want. But we're going to focus on these two. So yeah, as like an extra thing, you can code bubble up. But yeah, heapify is the one that's not talked about, and it's probably the most complicated of them all. So that's what we'll focus on, and then we can do talk about some follow-ups and stuff. Also, so you can do this heap sort in constant space. And the way it works, briefly, just to say, is essentially when we have a heap, like let's say this is our heap, whenever we pop off a node, we can say like, okay, we're going to pop this node, we're going to take the last node and put it in the front, and then we can take the node we popped off and just put it at the very last index. And then we can just say like the length of our heap now is this, so we maintain some variable to be the length of our heap. So essentially we shrink the length of our heap with like some variable, but we actually just keep putting in the thing we pop off at the end. So then at the end, basically what's going to happen is our numbers are going to be backwards. So you'll have the smallest here and then the biggest here, and then you just do a reverse. I'm going to make a separate array just to make it simpler, but you can do it in place if you want to as like a follow-up as well. All right, so let's code Heapify first. And we're going to use bubble down, so it's just going to take an array. And so basically what you want to do is you want to call bubble down on nodes that have children. So we can say for let I equals math floor. So basically the first index with the child will just be the array length over 2 minus 1. So essentially, like, if we go back to this picture, let's say this array length is 1, 2, 3, 4, 5, 6, 7. The first 3 nodes will have children, and this is at node 2. So you just take the half, and then you subtract 1 because it's 0 indexed. So half minus 1, and like this. You can also, in your bubble down, you can call bubble down on every single node. It's fine, because on the root node it will just be an O of 1 as well. Like, that's totally fine. Essentially, we're going to call bubble down on array and the index. And now bubble down is going to be like the main function that has all the heavy lifting. So it's going to take an array, and it's going to take an index, because essentially we're taking some index on the array and then we're bubbling down. So we're going to keep bubbling down, but we have to make sure, like, when we're bubbling down, that the child is not out of bounds, right? For example, like if we go here, there is no child. So we can just calculate the children like this, and we could say, like, if these children are within the length, then we can bubble down. If not, we can just stop. So while I times 2 plus 1 is less than array length, and remember, this is the left child. So if it doesn't have a left child, it won't have a right child because it's left to right. So if it has a left child, we can try to bubble down. So we can get the left index here. So yeah, so left is I times 2 plus 1, and right is I times 2 plus 2. And we can just say the minimum element is, the minimum element of the children is left. So we can say min index equals left. And then all we have to do is just check, like, if the right node exists and the right value is smaller than the left, then we'll change this min index to right. So if right is smaller than array length and array right is less than array left, then we'll modify the min index. Okay. So this is like the smaller of the 2 children. And then we have to check, like, for our node, is it already smaller than the 2 children? If it is, we don't need to do any bubbling and we're just done. So if array at the min index is greater than or equal to our current value, we're just done. So return. And we're just going to be modifying this array in place, not returning anything. Otherwise, we need to swap whatever value we're at with the min index value and then recurse down there, or like loop down there essentially. So we can do this in JavaScript like this. Array min index, and I do a swap. Like that. So we do a swap, and then we just recurse down to that guy. Okay, so we'll just keep doing this, keep bubbling down as much as we can. Okay. So now we have to actually get our main heap sort essentially to do this. So we're going to make a new array. Like I said, you can do this in place, but I'll do it as a new array for simplicity. And we're going to heapify our original array, because remember, heapifying will turn it into a heap in O of n. So, and you can't do heap pushes and heap pops from a non-heap. Like, it needs to be a heap, so you need to like turn into a heap. And there's two ways to turn into a heap: either heapify the array or make a new array and heap push elements one at a time so it maintains the heap, but heapifies faster. So we can say while this array still has elements, then let's push the smallest element of this array on the result, because that's going to be like always the min element. That's guaranteed for a min heap. Then we need to take our last element and push it. Remember, the way to delete a node is you go like this, and then you take the last element and you put it up here. So array 0 equals array at the last element, which is over here. Then we're going to pop the last element because we just moved it to the front. And then we're going to call bubble down on that top node to see, like, does it need to get moved now? Because that's how you do a heap push. Or sorry, heap pop. Okay, so essentially this, and now we can return. All right, let's check. Okay, good. Okay. So as far as follow-ups you can do here, so like I said, you can code up the bubble up and the, so this bubble down is basically like this bubble down is used for the heap push. You could, or heap pop, you could code up a heap push and a heap pop separately. And then what you can do is you can just go do leak code problems that require a heap and just like use your own heap. So you can make a heap on the bottom instead of importing, use your own heap and try that. The other thing you can do is here, I didn't really specify like a comparator. So you can make like a heap class with a comparator function as well. Like maybe you pass in a comparator function and then that's how you determine like how your heap is made. So that's another thing you can do. But yeah, this is one that like is definitely good to know, and it's good to know for coding interviews, and it's good to code from scratch, like at least once, just to understand how all this works. So hopefully this is helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.